Hi everybody. In this video I want to do an example that illustrates both parts of sort of the field concept for magnetism. So in this example we have a long current which I'm labeling I1 and the current is heading down toward the bottom of the board. This current produces a magnetic field everywhere, including here. That field then exerts a force on this moving charge. So we have two expressions to work with. We've got to first deal with the production of the magnetic field that this thing produces right here, using the formula for the magnitude of the magnetic field due to the current of a long wire. And then we need to figure out the force on that moving charge using this expression for the vector force on a moving charge. So it's a two-step process. We've got to make sure that we don't confuse the concept of force and field. So we have something that's setting up a magnetic field, and then something else that is influenced by that magnetic field and experiences a magnetic force. All right, so let's carry this out. So first, we have to look at the magnetic field produced by this long current. So we've got a current heading down this way. We're going to assume that this is an infinitely long wire, or close enough to infinite that we don't care. All right, so we can find for the magnitude of the magnetic field due to that long wire has this expression where we'll replace I with I1, and R perpendicular is the perpendicular distance from the wire where we want to know the magnetic field. Now, we could do that in principle anywhere, but we want to know the value of the magnetic field right here where this charge is that's going to experience a force due to the magnetic field. So this charge is located at distance d from the current I1. So that's where we want to know the magnetic field. So the magnetic field magnitude at this location produced by this long current I1 will be B with no arrow because it's a magnitude, mu naught. The current producing the magnetic field is I1, so I'll plug I1 in there. And if we had numbers, we would plug the numbers in there. 2 pi, and this R perpendicular represents in general the perpendicular distance from the wire. So if we want to know the magnetic field here, I'd use this distance. If I wanted to know the magnetic field here, I'd use this distance. I want to know the magnetic field here because I want to find the force that that field exerts on this charge. If I want to know the magnetic field here, I need this distance, which I'm calling d. Great, so if we had the numbers, we would actually have a value in Teslas for the magnitude of the magnetic field at this point due to this current. Now, we need more than just the magnitude, we also need the direction. Now, for the magnetic field produced by a long wire or a wire segment, we can get the direction using a derived right-hand rule. Stick the thumb of your right hand in the direction of the current. Wrap your fingers in the direction of the magnetic field. And so basically, if you've got a wire, magnetic fields make circles around that wire. This just tells us which way the circles are going. Thumb in the direction of the current, fingers wrap around. In regions over here, the magnetic field is into the board. So I'm going to represent that this way with little X's. So magnetic field is into the board in this region. Over here, the magnetic field would be out. I'll represent out with little dots. That's just for completeness. This doesn't matter for our particular problem. We need to know the magnetic field right here due to this. We need to know its magnitude, which we have. Now we have the direction into the board. All right, great. Once we have this, we can now find the force on this moving charge. So we move over to this expression. This is the magnetic force on some charge q moving with velocity v due to some magnetic field produced by something else. So let me emphasize this. This is not the magnetic field produced by this charge. This is a magnetic field produced by something else, in this case produced by the long current. This is the force on the charge. That's different from this equation here. This is the magnetic field produced by the current. This is the force on the charge. All right, so this is an expression that describes the production of a magnetic field. this is an expression that gives the force that a magnetic field exerts on some moving charge. All right, so let's plug this in. Well, there's two things we need to consider. We need to consider the direction of the force on this charge, and we need to consider the magnitude of the force on this charge. To get the magnitude, we just take the magnitude of this cross product here. To take the magnitude of any cross product, a product of a scalar and a cross product, you first take the absolute value of any scalars out front. This charge could be positive or negative, so I need to put it in absolute value signs. And then I take the magnitude of this expression. To take the magnitude of any cross product, you take the magnitude of the first vector. So there's no arrow over that because it's a magnitude. Magnitude of the second vector, and then the sine of the angle between those two vectors. All right, this is not this. This is just the magnitude of this. All right, so let's figure out that magnitude. So let's plug in first. Well, so this charge, that's the force, that's the charge on which we're trying to find the force. So it's the charge of this. For V, that's just the magnitude of the charge's velocity. B, that's just this. This is the magnitude of the magnetic field in the location of the charge on who we're trying to find the force. All right, so this is the magnetic field magnitude at this location due to this long wire. So that's this. And then finally the angle. Now we got to be careful. I've shown a 30-degree angle in here. Well, that is a relevant angle for something. If this is my x-axis and that's my y-axis, I'm saying that the velocity of the charge at this instant is 30 degrees from the x-axis in the plane of the board. But that's not what this angle's about. This angle is the angle between the velocity and the magnetic field. So let's be careful. My velocity is this way, but my magnetic field is into the board. So basically, into the board and velocity, there's a right angle there. The angle between this and this is a right angle. Velocity, magnetic field, 90 degrees between them. So I have the sine of 90 degrees. Sine of 90 degrees is 1. So the magnitude of the force on this moving charge is just going to be the absolute value of the charge, the magnitude of the charge's velocity, and the magnitude of the magnetic field at the location of the charge due to this long current, which has this form, expression mu naught I1 over 2 pi d. And we could clean that up, but that's good enough. All right, now, if this velocity were in some other direction like that or like that, if it had a different angle than 90 degrees from the magnetic field, then we'd have a factor here other than 1. So I'm just going to put 1 for this sine factor, just to indicate that, you know, you could have other things here other than just this. All right, great. So that's the magnitude of the magnetic force on this charge due to the magnetic field produced by this long current. If we had values for the charge, the speed, the current, the distance, and we know this constant, we could then get a number in newtons for the magnetic force. We're just going to leave it symbolic here. But now we need to deal with the direction. All right, so to look at the direction, let's go back to the cross product. We get the direction from the cross product and the right-hand rule in the cross product. All right, so let's consider the direction of V cross B. So to get the direction of V cross B, we have to remember the magnetic field vector B is into the board. That's what these X's are representing. So I need to go V cross B. So put my fingers in the direction of V vector, curl them into the direction of the magnetic field vector, and this will be the direction of V cross B. Now I'm going to be careful. I'm just going to put a little dotted line. That's the direction of V velocity vector cross magnetic field. That's this. But we have a negative charge that's experiencing the force, and that's in our mathematical expression. So we have the negative of that direction, which would be in this direction. So the force, magnetic force on that charge, will be this way. That is, this direction is the direction Q, V cross B. All right, now, just some comments on that direction. You know, it's possible with your fingers to be all sloppy. Is it this way? Is it this way? Remember, the cross product of any two vectors is guaranteed to be perpendicular to both the vectors in the cross product. So, the only two directions in the universe that are perpendicular to the velocity and the magnetic field are this direction and this direction. The right-hand rule just gives you the difference between those two directions. So, V cross B is this way. I know that this must be then 90 degrees right there. So if I wanted to measure from the x-axis, I'd have 30 degrees plus another 90 degrees, or 120 degrees from the x-axis counterclockwise in the xy plane, if I wanted to specify it that way. Of course, that's just the direction of V cross B. The charge that's experiencing the force is negative, so we've got the negative modifier of that, and we get this force in this direction, which also has to be perpendicular. So we could say, well, this is in the xy plane 90 degrees clockwise from the velocity, or 60 degrees clockwise in the xy plane from the x-axis. All right, so hopefully that illustrates how to use both expressions for finding the magnetic field in terms of a magnitude and a right-hand rule direction, and putting that information together with our force expression for finding the force, the magnetic force on a moving charge. So a two-step process. There's one thing, this current in this case, which is setting up a magnetic field, and then that magnetic field is exerting a force on this moving charge. Thanks for watching.